Good morning, or afternoon, or evening, depending on when you're watching this video. Today we're going to be learning about theorems for roots of polynomial equations. And let me just give you a disclaimer right now that this section can be difficult, so make sure that you are rewinding or pausing when need be to make sure that you catch all of the information. So the first theorem that we have today is the rational root theorem. And that just brings in a whole other slew of situations. For example, do you know what a rational number is? Maybe you do, maybe you don't. A rational number is basically a fractional number, a number that can be written as a fraction. Things like 2/3 or 1/2, 5/7. These are all rational numbers. But also things like 5 or 7. Which we don't normally consider fractions, but if you put the denominator as 1, then they can be considered fractions. So basically, all the integers and all the fractions are rational numbers. And that's important because this is a rational root theorem. And roots are basically x-intercepts, as we learned in the previous sections. The word root, solution, factor, they're all the same thing. So the word root shouldn't scare you. It's just asking for an x-intercept for the zero of the polynomial. And the other thing that's weird about this theorem is the word possible. You've seen here that I highlighted it. Possible. You know what possible means? It means that it could happen, but it doesn't mean that it's necessarily going to happen. So it is possible for a polynomial to have no rational roots. So the rational root theorem is only giving us a possibility of what it could be. And as we go through the problem, I will explain that a little bit further. There is a formula for the possible rational roots, and it is P over Q. And you're probably wondering, what's P, what's Q? Well, P is the constant term, and Q is the leading coefficient. So in our case, P is right here, the constant term. And Q is the leading coefficient, which in our case is a 1. That is going to be Q. All right? So what we want to do is we want to make a fraction, because it's rational, a fraction out of those two numbers. So we're going to get -3 on top and a +1 on the bottom. Then, as you can see, it says factors of the constant term. What are the factors of -3? Well, because 3 is a prime number, the factors of -3 are plus or minus 1 and plus or minus 3. It is important that you put the plus or minus because, for example, you could have a +1 times a -3, and that would give you -3. Or you could have a -1 and a +3, and that will also give you -3. So it is important that you include the positives. Now, for 1, what are the factors of 1? That one's easy. Plus or minus 1. And you're still not done yet. At this point, you actually have to go and divide everything out. Now, in this case, because there's a 1 on the bottom, we're going to get an easy situation where we're going 1 divided by 1 is still 1. And then 3 divided by 1 is still 3. But it is possible for you to have a 2 down here, and then you would have to go 1/2, 3/2. Does that make sense? And maybe in the next example, we'll show you how that works. But in this case, what I am saying, what this theorem is saying, is that we have a possibility of 4 rational roots. +1, -1, +3, and -3 are possibilities for rational roots. But we're still not sure that they're actually going to be roots at all. It's just that if there is a rational root for this polynomial, then it has to be in this list. So the rational root theorem basically gives us a list of possibilities, and then we have to test them. And how do we test them? We test them with synthetic division. Because we know from before that if you divide and you get a 0 remainder, then in fact you are a factor and therefore a root. So we're going to start with the +1, and we're going to do synthetic division here, so the coefficients of the terms are 1x cubed, 1x squared, -3x, and -3 for my constant term. And we're just going to apply synthetic division. 1 times 1 is 1, 1 plus 1 is 2, 2 times 1 is 2, 2 minus 3 is -1, making this a -1, and we get -4. This is not 0. Therefore, +1 is not a rational root. Then we're going to try the -1. have to do some erasing here, get rid of some numbers there. And we have 1 times negative 1 is negative 1, 1 minus 1 is 0, 0 times negative 1 is 0, 0 plus negative 3 is negative 3, negative times negative is positive 3, and then we get 0. Ding, 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 ding. That means that negative 1 is in fact a rational root. But is it the only root? We don't know. We're going to go ahead and put negative 1 over there for now, and we're going to try positive 3. I get rid of this guy real quick. Let's try the positive 3. Again, we have 1, 1, negative 3, negative 3. 1 times 3 is 3, 3 plus 1 is 4, 4 times 3 is 12, 12 minus 3 is 9, 9 times 3 is 27, and we get 24, which is not 0. So 3 is not a rational root. And then we try one more time with the negative 3. So 1 times negative 3 is negative 3, negative 3 plus 1 is negative 2, negative 3 times negative 2 is positive 6, 6 minus 3 is 3, 3 times 3 is negative 9, and we get negative 12. And again, we don't get a 0 remainder. Therefore, after all this division, these are the only possibilities. Okay, so because 5 didn't appear in this list, there's no point in checking 5. This is the only list that will give us possible rational roots. So again, if this polynomial is going to have rational roots, they have to be in this list. Once we've exhausted this list, then we can safely say that the only rational root, excuse me, the only rational root for this polynomial is negative 1. All right, so now we're going to ask you to try one on your own. Find the rational roots of this polynomial. Okay, so now, example 2 is very similar to example 1. I will kind of go back here so you can see what's happening. You will notice that in the do-it-yourself number 1 and in the example I did, the key word here is find the rational roots. Okay, so I did not find imaginary roots. I did not find irrational roots. I only found the rational roots, which was negative 1. Okay, well, what you will notice now, and by the way, in the do-it-yourself also it says rational. It's asking you for the rational roots. Okay, so it doesn't want the imaginary ones, it doesn't want the irrational ones, just the rational ones. But now what's different is that you will see that it now says all. It says find all the roots. Now it doesn't have to say all, but it does have to not say rational. If it doesn't say, like if it just says find the roots, when it says find the roots and it's not specifically saying find the rational roots, then it means that you want to find all of them. So in this case, I need to find all of them, including the rational ones. Okay, so, sorry, that's the bell there. So what's going to happen is I am going to do that. Again, we're going to do P over Q. Remember that P is the constant term, which in this case is negative 1. There is my P. And divide that by Q, which is the coefficient, the leading coefficient. So there's my Q. So now we want the factors of 1, which in this case is just plus or minus 1, and the factors of 2, plus or minus 1, plus or minus 2. Okay? And so now we're going to get all of the numbers by saying 1 over 1 is 1, 1 over 2 is 1/2. So again, we have 4 possibilities for rational roots. Positive 1, negative 1, positive 1/2, and negative 1/2. Okay? So as you can see, we're going to start the process much like we did in the previous example. Which one of these 4 is actually going to be a rational root, or are all 4 of them going to be a rational root? That's the question. So we're going to do synthetic division again. And this time we have a 2, a negative 1, a positive 2, and a negative 1. So we've got 3, 2, 1, none. Okay. And this is always going to go like that. Okay. So we're going to start with the positive 1. So 2 times 1 is 2, 2 minus 1 is 1, 1 times 1 is 1, 2 plus 1 is 3, 3 times 1 is 3, and 3 minus 1 is 2. So because I don't get 0, that means that positive 1 is not a rational root. Now I'm going to try negative 1. So 2 times negative 1 is negative 2. Negative 2 and negative 1 is actually going to be, I'm going to erase here. Negative 2 and negative 1 is actually negative 3. Negative 3 times negative 1 is positive 3. So I need to erase some of these extra numbers here so that we can do this. So I've got positive 3, 3 plus 2 is 5, 5 times negative 5, and we get negative 6. Again, not 0. So we want to then exclude positive and negative 1. And I'm erasing it so I can do this again. And this time we're going to try negative 1/2. And then after that we'll try positive 1/2. So bring the 2 here. 2 times 1/2 is 1. That's going to be negative 2. Negative 2 times negative 1/2 is going to be, again, positive 1. That's going to be 3. This is going to be negative 3/2. And this is going to be negative 5/2. Again, not 0. So now we're going to try positive 1/2. So you can see that I have to keep trying all these possibilities until I get one. So it's kind of tedious, but it is the only method that we have. So now we're going to try positive 1/2 and hope that we get lucky. So 2 times 1/2 is 1. 1 minus 1 is 0. 0 times 1/2 is 0. 0 plus 2 is 2. 2 times 1/2 is 1. And finally, we get our 0 remainder. That means that 1/2 is a rational root. And now you're probably wondering, well, okay, I know that one of the roots, part of my answer for the roots is that x equals 1/2. That's the rational root, but it wants all the roots. So it wants the imaginary ones or the irrational ones. So how do we do that? Well, you will recall that when you use synthetic division, these are the coefficients of a cubic. So this last row here are the coefficients of 1 degree less, which is a quadratic. So now what's happening is you have these guys are a quadratic. And we learned how to solve quadratics a long time ago. So once I find the 1/2, I can actually use previous methods to figure out the quadratic. So this is actually going to be 2x squared plus 0x plus 2. Now this is not a very complicated problem to solve. I can actually subtract the 2 to both sides, making it a negative 2. Then divide by 2 on both sides, giving me a negative 1. And when I square root, because it's negative, I get plus or minus I. So you can see that the only rational root was 1/2. The imaginary roots are positive I and negative I. And now I have found all of the roots, the rational and the imaginary. So now I'd like for you to try one on your own, or 2 on your own actually. And again, remember that in this case it's asking for all the roots of each equation. Okay. So the next couple of theorems that are in your book are about irrational and imaginary roots. We kind of already touched on imaginary in the last example. Something that you probably didn't notice, but they always come in pairs. So when I got positive I as a 0, I also got negative I as a 0. They always come in pairs, and so do irrational roots. And maybe at this point you're probably wondering, I don't even remember what irrational is. Irrational is basically when you have square roots of things. Numbers like pi are irrational, but for our purpose right now, you're thinking about numbers like root 5 or 2 minus root 3. These are considered irrational. And you will recall that these numbers basically happen when you use the quadratic formula sometimes. You end up with answers like, plus or minus the square root of whatever. So that's what it means when it says irrational roots. Imaginary also comes from the quadratic formula when you have negative underneath the radical. But the 2 theorems in this lesson are basically saying that when you have an irrational root, when you have an imaginary root, they will always, 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 always come in pairs. So it is impossible to have root 5 as a 0 and not have negative root 5 as a 0, because they always come in conjugate pairs. Okay? So, for example, if I give you if you have a polynomial that has given roots 1 plus root 3 and negative root 11, it's asking you to find 2 additional roots. This is very simple, because since 1 plus root 3 is a 0, then its conjugate pair must also be a 0. And it's that simple. The 2 additional roots would be 1 minus root 3, which is the conjugate of 1 plus root 3, and also positive root 11, because positive root 11 is the conjugate of negative root 11. Remember, conjugate just means the opposite. Okay? So now you can find 2 additional roots for this example. And then I have one for you that is the imaginary case. Again, very similar. In this case, given roots are 3 minus I and 2I, and it wants you to find 2 additional roots. Well, the conjugate of 3 minus I is 3 plus I. So that is the other root. And the conjugate of 2I is negative 2I. So there you go. It's that hard. Those are the 2 additional roots for this example. And so I would like for you to try that little guy, finding 2 additional roots. And then our last example is this guy. This is probably the most complicated of them all. And so just kind of bear with me here. It wants you to find a 3rd degree polynomial equation with rational coefficients, so the coefficients can't have i's in it and they can't have square roots in it. It's got to be a fraction or an integer that has these roots, 3 and 1 plus I. Well, the first problem is it wants a 3rd degree polynomial and you only have 2 zeros. But luckily we just learned that if you have an imaginary root, that it has to come in a pair. So even though they didn't tell me that it has 3 zeros, I'm supposed to know that 1 minus I is automatically another root, because it's the conjugate of 1 plus I, and they always come in pairs. The number 3 is not imaginary, it's not irrational, and it doesn't have to come in a pair. So now I have 3 roots. And you will remember that, hopefully you will recall that we know that if I tell you that x equals 5, 2, and 3, that we can go backwards and factor these out as x minus 5, x minus 2, x minus 3, and then, FOIL it and get a polynomial at the end. We've done this before with normal or rational zeros, okay, integer zeros. So now we're just going to have to do it with imaginary ones. It's a little bit trickier, but still very doable. So I'm going to show you that next. In this case, I know that I have my zeros are x equals 3, x equals 1 plus I, and we generally put parentheses around that number to kind of keep it together. And I also know that x equals 1 minus I. Okay? And like before, what we can do is we can subtract the 3 to the other side, making it x minus 3 equals 0. And this would be x minus 1 plus I equals 0. Try really hard not to distribute that negative. And here I could get x minus 1 minus I equals 0. So again, I'm just moving those over to the other side. Once I've done that, I can actually write them all out as factors. There we go. So now we can write them out as a product. And I will tell you that it is probably easiest to start with the imaginary portion here. In other words, don't try to distribute or don't try to multiply this factor by this factor first. Excuse me. It is far easier to multiply these two first because they have the imaginary components in them. Now this is going to be kind of tricky, so just watch carefully. If you need to pause, rewind, do it. There's a lot going on here. So I'm going to FOIL, and I'm going to treat this as one whole number by itself. Okay, and we're going to FOIL. So I'm going to erase this here so I can do my FOILing here. And FOIL says f is first times first, so x times x is x squared. The O is outside times outside, so it's going to be x times negative 1 minus I. So it's going to be negative x, because of the positive x and the negative 1, negative x times 1 minus I. Notice that I am not distributing anything yet. The I is for inside times inside, and again, you have a negative and an x, so negative x, and this time it's 1 plus I. And then last, you have L, so last times last is going to be negative times negative, which is positive, 1 plus I, and 1 minus I. Okay? So that's pretty much the FOILization there. Now it's actually okay to go ahead and distribute here. Negative x times 1 is negative x. Negative x times negative I is positive ix. Here you have negative x times 1 is negative x. Negative x times positive I is negative ix. Okay? And then here, you might remember from before that you have basically a plus bi, a minus bi, and again, in previous lessons, previous sections, we learned that when you have a plus bi and a minus bi, that's always a squared plus b squared. Remembering that the b is the coefficient in front of I. So in this case, the coefficient in front of I is a 1. So really what it's saying is 1 squared, because a is 1, plus 1 squared, which is actually 2. So at the end of the day, all of this comes down to plus 2. All right? Okay, and of course, you still have your x squared from before. Now we can start simplifying some terms, and I'm sure by now you're probably thinking, oh my goodness, what just happened? If you need to go back, go ahead and go back. But you have a positive ix and a negative ix, and they cancel. Then you have a negative x here and a negative x there, making it negative 2x's. So you get x squared minus 2x plus 2. So isn't that nice? You actually ended up foiling this big ugly mess, and it turns out to be a nice simple quadratic. But don't forget that you still need to multiply it by x minus 3, and that is our final step that we're going to need to do. I'm going to get this out of the way here so you continue. So now we're going to basically take x times x squared minus 2x plus 2. Okay, I'm going to take the x times everything and the negative 3 times everything, so minus 3 times everything. And we're going to lastly simplify this, and we should be done. X times x squared is x cubed. X times negative 2x, negative 2x squared. X times 2, positive 2x. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is positive 6x. Negative 3 times positive 2 is negative 6. We combine our like terms, and we can finally leave an answer up here. We've got one term that has x cubed in it. We have two terms that have x squared in them. So negative 2 and negative 3 is negative 5x squared. We've got a positive 2x and a positive 6x, making it 8x. And lastly, we have the minus 6. So this is our final answer. It is a third degree polynomial because it has x to the third power, and it has rational coefficients because it's a 1, a negative 5, an 8, and a negative 6. All of those are rational numbers. And the roots are 3, 1 plus I, and 1 minus I. So at this time, you can try one on your own. And when you've done that, you have completed the lesson for today. Thank you for watching.